Okay, good morning. We started defining the semantics of Haskell, and in particular we were concerned with the question, what should we do with function types? So if we have an expression of a function type, to which actual function should we map it in the semantics? So what is the meaning of a function that we defined in Haskell? And well, of course we could say, well, functions from int to int are mapped to function expressions from int to int are mapped to functions from z bottom to z bottom, and then that's true, but we don't need all of these functions. We can restrict ourselves, and one restriction that we wanted to make is we wanted to restrict ourselves to monotonic functions, because if a function is not monotonic, then it is not computable. So it makes no sense to look at non-monotonic functions. And what does monotonic mean? Monotonic means the following. A function which goes from one domain d1 to another domain d2 is called monotonic if the following holds. If I have two arguments d and d prime, and d is less defined or equal to d prime, then, well, the same thing should still hold when I apply f. So f of d should be less defined or equal to f of d prime. So this is the meaning of monotonic. And, well, what is this good for? It will turn out that we need another restriction, an even harder restriction, which restricts the set of monotonic functions further. And we will need this in order to define the semantics of recursively defined functions. So if you think of a recursively defined function like factorial, what we will do in the end is we will define the semantics of factorial as the limes of a sequence of functions. So as the limes of a sequence of functions which is called a chain. For example, a chain like this. Here we had functions fact0, fact1, fact2, and so on. And they approximate the factorial function. So they get more and more closer to the real factorial function. The only problem is that there are certain values where these approximations are still undefined. So for example, fact0 is undefined everywhere. Fact1 is defined for numbers up to 0. So for x equals 0, it computes the factorial. For negative numbers, it computes 1, and otherwise it's undefined. And this one is defined for numbers up to 1. The next one is defined for numbers up to 2, and so on. So if we move further and further, we get closer and closer to the real factorial function, which is defined on all numbers. And the idea is that we will define the semantics of recursively defined functions as the least upper bound of such a chain of functions. So what's a chain? A chain is just a set of elements which you can order in such a way that they become more and more defined. So a set like this is a chain if you can order the elements such that d1 is less defined or equal to d2, d2 is less defined or equal to d3, and so on. And here's an example. All these functions, fact0, fact1, fact2, they are a chain because indeed fact0 is less defined or equal to fact1 for every argument. I mean, fact0 is not defined anywhere. Fact1 is at least defined for negative numbers and for 0. Fact2 is a little bit more defined than fact1. It's the same as fact1 for all numbers except the number 1. This is defined for 1, this is undefined for 1, and so on. So this set is a chain, and what we would like to do is we would like to look at the limes of such a chain, or more precisely, at the least upper bound of a chain. So the least upper bound is, well, it's an upper bound of this set, so it's greater or equal to every element in the set, and it's the smallest such upper bound. We call something like this least upper bound, and denoted by this symbol. So this is like the less defined symbol, but turned around by 90 degrees. And the least upper bound of this chain indeed is the factorial function. So it's fact, which is undefined for the argument undefined, which is 1 for negative numbers, and which computes the factorial for positive numbers. So this is what we would like to do. And then, of course, the question is, does such a chain always have a least upper bound? So no matter which chain I have, do I always have a least upper bound? Well, that's what we would like to have, and therefore we require that our domains and our orderings should have this property, and if they have this property, we call them complete. So we say that if I have a reflexive partial ordering on some set D, we say that the ordering is complete if it has the following two properties. First property is there must be a smallest element in D, and we denote the smallest element by bottom index D, and we omit the index if D is clear. And moreover, every chain must have a least upper bound. So if I have some subset of D, some subset S, which is a chain, so I can order the elements such that they become more and more defined, then there must also be a least upper bound of this chain, and this least upper bound must be contained in D. So this will be the property that we will require for all our domains. So for the domain of integers, for the domain for tuples, for the domain for functions, they should be complete. So every chain should have a least upper bound. Now let's check whether the domains that we looked at up to now are really complete. So whether every chain has a least upper bound. And so indeed all the domains that we regarded up to now all these domains are complete. Well, you don't have to believe this. You can prove this. So let's prove this. And that's theorem 2.1.13, which speaks about the completeness of the domains. So what were the domains for the base types? So for integers, booleans, characters, floating point numbers. Well, these were these very simple domains where we just had the objects you were thinking of, for example, the integers, plus one extra element bottom, which stands for undefined. And all these domains are complete. That's the statement of part A. In fact, we can even state something stronger. We can say that as soon as we have a partial reflexive order, so every partial reflexive order which has a smallest element, so with smallest element, and which has the property that the corresponding domain is flat, or in fact it's sufficient to require that every chain is finite. So where every chain is finite, every such partial order is complete. Is a CPO, a complete partial order. So this is the abbreviation of complete partial order. And so that means if we look at our base domains like Z bottom, I mean every chain there has at most length 2. So something like bottom 0. That's a chain, and we cannot make it any longer because 0 is completely defined. There is nothing that is more defined than 0. And bottom 5 is, of course, another possible chain. So thus, the flat base domains, so the one for the integers, the one for the booleans, the one for the characters, and the one for the floating point numbers, they are all complete. Because they obviously have a smallest element, and every chain has at most length 2. Yes?
But the smallest element, you assume that this is the element who is the less defined than the others.
Yes. So, I mean, for Z bottom is the bottom element of Z bottom plus the integers. And the order that we regarded here is the one where we have D is less defined or equal to D prime if D is bottom. And if this is the set with this order, then it's obvious that this order has a smallest element, namely this one. And it's also obvious that every chain has at most length 2. Okay, this we will prove. But let's finish this theorem. So these were the domains for these primitive predefined types. Now, what were the domains for tuples? Well, the corresponding Cartesian products. And indeed, here we have completeness as well. So So if this is a complete partial order on D1, it's a complete partial order on D1, and so on, and this is a complete partial order on Dn, then the less defined or equal relation on the Cartesian product is also complete. So then the order which compares tuples component-wise is a complete partial order on D1 cross Dn. So in other words, this domain, which we regard for tuples, is also complete, provided that the domains that we regarded for the components were complete. And the same thing is true for functions. So what did we do for functions? Well, if this is complete on D2, then the less defined or equal relation on the functions from D1 to D2 is a CPO on the set of functions from D1 to D2. So everything we looked at is complete. Now let's prove it. Okay, so in part A, we look at an arbitrary domain where every chain is finite, provided the domain has the smallest element. So it has the smallest element, so we only have to prove the second property of complete orders, namely that every chain has a least upper bound. So let's look at the chain, and here every chain is finite. So the chain looks like this. It consists just of finitely many elements. So let this be a chain. And, well, if it's a chain, then I can order the elements. So let's say I can order them like this. So D1 is less defined than or equal to D2, and so on. And this is less defined than Dn. And the claim is every such chain has a least upper bound. What's the least upper bound of this chain? Dn, right. Then the least upper bound of S is Dn. Now, why is this true? So, in case you don't believe this, well, why is it an upper bound? Well, for every element in here, for every di, I have that Dn is an upper bound of this. So for all I from 1 to n. Well, why is this true? Well, because of transitivity. Since this relation is transitive, we clearly have that every element here is less defined or equal to Dn. So since this is transitive, so clearly Dn is an upper bound of S. And why is it the least upper bound? So this was the part that is an upper bound. Now let's prove that it is the least upper bound. Well, let's assume there's another upper bound. So let E be another upper bound of S. Now we have to show that Dn is less than or equal to E. Well, why is this true? Right, because Dn is element of S. So since Dn is contained in S, if E is an upper bound of S, it must also be greater or equal to Dn. So yes, Dn is less than or equal to every upper bound of S. Okay, so this is true. and it wasn't too difficult. Now, let's look at part B. In part B, we have to prove that these less defined or equal relations are complete on these Cartesian products. So the first thing is we have to show that there's the smallest element. What's the smallest element of d1 to the n? So the smallest element of d1 cross dn is, well, it must be a tuple with n components, and since the components are compared, and since the tuples are compared component-wise, this will be the tuple which has the smallest element of d1 in the first component and the smallest element of dn in the last component. So this is the smallest element of d1 cross dn. And so there is the smallest element, and that's easy to see. What we still need to prove is that every chain of tuples has a least upper bound. Okay, so let's do it as we did it in part A. So let's regard a chain. Now the chain must consist, well, it's a subset of d1 cross d2 cross dn, so it's a set of tuples. So it looks like this. d11 to dn1 and d12 to dn2 and so on. And the chain could be finite or could be infinite. Well, if it's finite, it's trivial that there's a least upper bound. If it's infinite, it's maybe not so trivial. So it could be finite or infinite. And it's a chain. And chain means I can order the elements by their definedness. So, for example, d11, so this first tuple is less defined or equal than the second tuple, d12 to dn2, and so on. And now I have to prove that there's a least upper bound of this chain. And what I know is that for the components here, so for capital D1 and capital D2 and so on, they are complete. So there, every chain has a least upper bound. And the question is, why does this chain have a least upper bound as well? So any idea? Mm-hmm.
You can look at the component, at the tuples components-wise, and take all the components of the tuple, and there you have the upper bound. And now you can put this together to one upper bound.
Right, exactly. So I can look at the tuples component-wise. So let's look at the first argument. So if this holds, then in particular, the first argument must get more defined or equal in every step. So according to the definition of less defined or equal for tuples, I have that this component is less defined or equal than the first component here, and so on. And this holds not only for the first component, but also for the second and also for the last component. So also here, sorry, this was the wrong way around. So also here, I want the nth component in tuple number 1, and I want the nth component in tuple number 2, and so on, and the nth component in tuple 3. Okay, and indeed, since I know that, well, this is a chain from capital D1. So this is a chain from D1, and this is a chain from Dn. And I know that this is a complete partial order on D1, and this is a complete partial order on Dn. So this has a least upper bound, and this has a least upper bound. So since these orders on D1 and Dn are complete, I know that this chain here, let's call it S1. So D11, D12, and so on. This has a least upper bound. So some least upper bound S1. And the same thing is true for Sn. So this consists of all the nth component. The nth component of tuple 1 and the nth component of tuple 2 and so on. This has a least upper bound, well, the least upper bound of Sn. And now why does the whole thing have a least upper bound? Well, the least upper bound of the whole set S, I can get this by taking the least upper bound of the first components, the least upper bound of the second components, and so on. So this is the least upper bound of S1 and the least upper bound of Sn. And that this holds is something that we proved in the last lecture, or in the lecture before. This was proved in lemma 2111a. So there we proved that if you want the least upper bound of a chain of tuples, you can look at this component-wise and build the least upper bound for every component. And so we've shown that indeed, if these least upper bounds exist, then this least upper bound exists as well. And so completeness of the tuple domain follows from completeness of the component domains. Okay, and well, I will skip the proof for part C because this is completely analogous to the proof of part B. So this is analogous to B. Okay, so we can be relaxed. Every chain has a least upper bound. At least this is true for the domains that we look at. Okay, now still the question remains, if I want to define the semantics of recursively defined functions by building such a chain like fact 0, fact 1, fact 2, and so on, how do I get from fact to fact 0, fact 1, fact 2, and so on? And to describe this, we need another property of our functions. So monotonicity is not enough, but we will introduce another property which is more restrictive than monotonicity. So introduce another property in addition to monotonicity. In addition to monotonicity, and this property will be needed to define the semantics of recursively defined Haskell functions. Recursively defined Haskell functions. And this property is the property of continuity. And maybe before I define this, I will try to depict this by some small graphic. So what continuity means is the following. It means that if you have a chain, so suppose we have some chain. So D1 is less defined or equal to D2, D2 is less defined or equal to D3, and so on. And this might take forever. Well, we know that the domains that we look at are complete, so we know that every chain has a least upper bound. So for such a chain, we could build the least upper bound, and then we get some least upper bound D. And if we now want to apply functions to least upper bound. So suppose we want to apply some function f to this least upper bound. So here we apply some function f. Well, then we get f of d. And now continuity means that instead of first taking the least upper bound and then applying f, we could also do it the other way around. So if f is continuous, then this means instead of first building the least upper bound and then applying f, we could do it the other way around. We could proceed the other way around. So let's do it the other way around. The other way around means we first apply f and then we build the least upper bound. So if we first apply f, we could apply f to d1 and then we get f of d1. And we could apply f to d2 and then we get f of d2. And we could apply f to d3, of course, and then we get f of d3. And, well, what is the relation between f of d1, f of d2, and f of d3? Well, as long as f is monotonic, we know that since d1 was less defined or equal than d2, then f of d1 should also be less defined or equal than f of d2. That's monotonicity. So if f is monotonic, we know that this thing is more defined or equal to this. And similarly here. And so by applying f, we again get a chain. And now if f is continuous, then this means if we take the least upper bound of this chain, then we arrive at the same result here. So in other words, if f is continuous, then this means the things that I do by the solid arrows are the same than the things that I get by the dotted arrows. So I can, moving around this way is the same as proceeding around this way. So first building the least upper bound and then f is the same as first applying f and then the least upper bound. If this holds, then f is continuous. Okay, let's define this formally, but this should illustrate the intuition. Okay, let's define this formally. So this is definition 2.1.14, and it defines the notion of continuity, or what does it mean for a function to be continuous. So we have two domains, d1 and d2, and we have a function from d1 and from d1 to d2. And the less defined or equal relations should be complete, both for d1 and d2. So let this be a CPO on d1, and let the less defined or equal relation on d2 be a complete partial order on d2. And now we have a function from d1 to d2. So a function f from d1 to d2. Such a function is called continuous. Is continuous, stetig in German, if and only if the following holds. For every chain, so a chain like this, d1, d2, d3, and so on, if for every chain S from d1 we have the following. If I apply f to the least upper bound of the chain, so this d1 to dn is the chain, d1, d2, d3 is the chain, and d is the least upper bound of the chain. So if I apply f to the least upper bound of the chain, so this is what I call d up there, then this is the same as applying f to every element of the chain and then building the least upper bound afterwards. So if we apply f to every element of the chain, so this is the set for all elements from S, I take f of d and I take the least upper bound of this set. So these two things should be the same. And the set of all continuous functions from d1 to d2, of all continuous functions from d1 to d2 is denoted d1 to d2 in angle brackets. Now, if you look into the literature, this is typically not denoted like this. So if you look into books, then typically this is not denoted with angle brackets, but with square brackets. But in the lecture, we will use this notation instead, because this could be confused with the list of functions from d1 to d2. I mean, in Haskell, we use square brackets for lists, and this has nothing to do with lists. This is just the set of continuous functions. And so to avoid this confusion with Haskell notation, I will use angle brackets, but if you look into books, you will find square brackets.
Could you show a function that is monotonic but not continuous?
No. Yes. A function that is monotonic and not continuous.
To me, it seems as if this code is also monotonic.
Okay. That's what you might think, but in about 3 minutes, I will show you a function that is monotonic and not continuous. So this is harder. So it will turn out that every continuous function is monotonic, but not vice versa. So we will see in a minute. Okay, so this is in the literature. Maybe to a short notation for this. So instead of writing f of the least upper bound of S is the same as the least upper bound of, well, this set where we apply f to every element in S. Instead of this, we sometimes also write f of S. So this means apply f to every element in the set. So instead of writing this, we sometimes just write the set here, and it means apply f to every element in here and take this new set. So it's something like map if you want. And if you write this notation instead of this notation, then continuity looks very nice, because then you can write continuity like this. And it shows that you can switch the application of f and least upper bound. So instead of first applying least upper bound and then f, you could also first apply f and then the least upper bounds. So this is a very short way of writing it, which makes very clear what continuity is all about. Okay, now some examples. First, some very easy examples, and then an example which is monotonic but not continuous. So let's look at some examples and look whether the functions are continuous or not. Now, the first example is the easiest one. Let's look at, let's show that every constant function is continuous. So every constant function is continuous. Now, why is this the case? So a constant function looks like this. It goes from d1 to d2, but it gives you the same result no matter to which element you apply it. So f of x is some e for all x from d1. So this is a constant function which always returns e. Now, why is this function continuous? So let S be a chain from d1. And we have to prove that if I apply f to the least upper bound of S, so to show that this is the same as applying f to every element in S and building the least upper bound afterwards. Okay, so what is this? We apply f to the least upper bound of S. Well, I don't know what the least upper bound of S is. It's some element from d1, but f returns e for every argument. So no matter how this looks like, this will be e. And what is this? Well, here I apply f to every element in S. So if I apply f to the first element of S, I get the result e. If I apply f to the second element in S, I get the result e, because f always returns e, no matter what argument I take. So this thing is the set containing only e. And now I have to take the least upper bound of this set, which is obviously e. I mean, it's the only thing that is in this set. So this whole thing is e. And indeed, here we have e, there we have e. So yes, f is continuous. Okay, I mean, this was a particularly simple function. Let's look at a slightly more involved function and check whether it is continuous as well. Let's look at the identity function. So the identity function is also continuous. Identity function is continuous. Well, why? So what's the identity function? It's a function I which goes from some domain D to D again, and it returns the identity. So with I of x is x for all x from D. So I want to show that this is continuous. So what do I have to show? Well, let S be a chain. And now I have to show that I of the least upper bound of S is the same as applying I to every element in S and taking the least upper bound afterwards. Now, why is this true? So the least upper bound of S is some element, some object. Okay, I don't know how it looks like, but it is some object. If I apply I to it, what will be the result? Well, I just is the same upper bound, right? It's just the identity. So this will be the least upper bound of S. Okay, now let's look at this. Here I apply the identity to every element in S. So what will be the result of this? S, right. So I apply this to every element in the set. Well, identity changes nothing, so this will be S. So the whole thing here is the least upper bound of S. Well, I have the least upper bound of S here and there, so it's equal, yes. So the identity function is continuous. Okay, now let's look at the function that is not continuous but monotonic. And, well, it will turn out that all computable functions are not only monotonic but also continuous. So we need something that is not computable, and if it's not computable, it's a slightly more strange function. But it's the function which checks for totality. So the totality function. So what does this function do? It's a kind of termination prover. It gets a function as input, and it checks whether this function is terminating everywhere. And if it's terminating everywhere, it says yes. And if it's not terminating everywhere, it may be undefined. So this totality function looks like this. It takes, let's look only at integers. So it takes a function which works on integers, including bottom. So it takes a function from z bottom to z bottom, and it checks whether this function is defined everywhere. And if it's defined everywhere, it returns, well, 0, and if it's not defined everywhere, it returns bottom. So it goes to z bottom with the definition is as follows. So G takes a function f as input, and it checks whether f is total. So G of f is 0 if f is total, and otherwise G of f is bottom otherwise. So we don't require G to be defined everywhere. So it's okay for G not to terminate, but it has to check whether f is total, and if f is total, it should find this out and terminate and return this result to us. So this would be, well, it doesn't solve the halting problem in the sense that this G always terminates. It's okay for G to not terminate, but if f is total, it should find it out. So it's a kind of semi-decision procedure for totality. So this returns 0 if f is defined everywhere. So f of x is not undefined for all x except bottom. So for all x from from Z. And otherwise, G returns bottom. Now let's think about, is G computable? Could you write a program which computes G? Well, at first sight you might think, why not? I mean, what could G do? If f is computable, it could call f on the argument 0. Now if f0 doesn't terminate, well then our implementation would also not terminate, so it would return bottom. That's fine. If f0 terminates, we will find this out in finite time. And now we try f of 1. And if f of 1 doesn't terminate, then, well, G doesn't terminate either, so that's good. But if f1 terminates, we find this out in finite time, and then we try f of 2, and so on. And so now you see the problem. We have to test f on every possible argument. And once we have tested f on all infinitely many arguments, on 0, 1, minus 1, 2, minus 2, then we can stop and return 0. But we need infinitely long to test f on every argument, so this is not really computable. So G is not computable because one would have to test f of x on all infinitely many integer numbers x. And well, what G would do is, G is a semi-decision procedure. If f is total, then G returns yes, or 0, f is total. And if f is not total, then G doesn't terminate. And so G is a semi-decision procedure for totality, but totality is not semi-decidable. Is not semi-decidable. So the difference between decidable and semi-decidable is, a problem is decidable if you can write a computable function which always terminates and which returns yes or no depending on whether the problem is true or not. And semi-decidable means you can write a function which may be non-terminating, but whenever the problem is true, it has to terminate and say yes. And if the problem is not true, well, then your semi-decision procedure may be non-terminating. So semi-decidable is something weaker, and termination on its own. So the question whether a function is terminating for one specific argument, this is obviously semi-decidable because you can just execute the function. And, well, if it terminates, then your checking function will terminate as well. But here we have the problem, we don't want to find out whether f is terminating for one particular argument x, but we have to find out whether f is terminating for all arguments x. And there are infinitely many of them. So testing them all is not possible in finite time. And therefore, this is a harder problem than just termination on one argument. And this problem is not even semi-decidable. OK, I didn't prove that it's not semi-decidable, but the proof for this is more involved. But you can believe me that it is not semi-decidable. So this is a non-computable function. And now we will see that this function is monotonic, but not continuous. So G is monotonic, but not continuous. Why? So, well, why is G monotonic? So suppose that, well, G operates on functions. So suppose that we have two functions and one is more defined than the other. So let's have f1 is less defined or equal to f2. Now what does that mean? And we want to show that G of f1 then is less defined or equal to G of f2. Now there are two possibilities. The first possibility is that f1 and f2 are equal. Yeah, I mean, if they are equal, then this will be equal as well, so that's trivial. So if 1 is equal to f2, then clearly g of f1 is equal to g of f2. And therefore also less defined or equal. And otherwise, so if this holds and they are not equal, well, then they must differ on some argument. And the only way that they can differ, if they are equal on all integers, if this holds for all integers, so I don't care about bottom, but for the integers they should be equal. If they are equal for all integers, I mean G only checks for the behavior on the integers. If they are both total on the integers, then g of f1 will be 0 and g of f2 will be 0. And if they are both not total on the integers, then g of f1 will be bottom and g of f2 will be bottom as well. And otherwise, if they are not equal on the integers, but f1 is less defined or equal than f2, then the only possibility is that there is some integer where f1 is not defined. So otherwise, there is an x from the integers with f1 of x is bottom. So then the only possibility is that f1 is not total. And if f1 is not total, then g of f1 is bottom. So g of f1 will be bottom. And therefore, g of f1 is less defined or equal than g of f2 because bottom is smaller or equal to anything. So this will be less defined or equal to g of f2. So this is really monotonic. If I make f more defined, well, then either they are both not total, or both partial, or f is partial and f is total, and in all cases, g will be monotonic as well. So g is monotonic, but g is not continuous. Why is g not continuous? So my claim is that g is not continuous and, well, to show this, I give a counterexample. And to this end, I will again regard these functions fact0, fact1, fact2 that we had before. So my counterexample is this chain. It's fact0, fact1, and so on. Now, what about the totality of these functions? Now, the question is, does the function map every integer number to something that is not bottom? Well, fact0 is clearly not total. It maps everything to bottom. So this is not total. What about fact1? Does fact1 map every number to something different from bottom? No, clearly not, because as soon as I have a number that is greater or equal than 1, it will be mapped to bottom. So fact1 is not total. And fact2 is also not total. If I have a number which is 2 or greater, it will be mapped to bottom. And similarly for fact3, fact4, fact5, and so on. If I choose a number that is large enough, then it will be mapped to bottom. So they are all not total. So this is not total, this is not total. They are all not total. And therefore, g of fact0 is bottom, and g of fact1 is bottom, and so on. And what's the least upper bound of this chain? It's this function fact. It's the function fact that you can see over there. And is the function fact total? Yes, the function fact is total. Every number is mapped to a number again. Only bottom is mapped to bottom. So fact is total. So this is total, and therefore g of fact is 0. And, well, this refutes continuity. Why? Because g of the least upper bound should be the same as applying g to every element in S. Now, if I apply g to every element in S, if I apply to fact 0, I get bottom. If I apply to fact 1, I get bottom. So for every element in S, here I get bottom. So this thing is the set containing only bottom. Well, and the least upper bound of this set is clearly bottom. And here, well, the least upper bound of this is fact, and g of fact is 0 because fact is a total function. So here we have 0. So here we have 0, there we have bottom. That's not the same. So g is not continuous. So what does that mean? That means that for continuity, the behavior of a function on the least upper bound of a chain should be derivable from the behavior of the function on the elements of the chain. So here's again, okay, part of this we didn't have yet. This again shows this, this diagram that we had before. And so if f is continuous, then the following must hold. If I want to know how does f behave on the least upper bound of a chain, well, then this should be computable from f's behavior on all the chain elements. So if I know what f does on d1, on d2, and d3, from this I should be able to infer what f will do on the least upper bound of the chain. And that's true for continuous functions, but it's not true for g, because if I know how g behaves on all the elements of the chain, then I cannot infer how g behaves on the least upper bound of the chain, because on all these elements of the chain, g behaves completely differently than g behaves on the least upper bound of the chain. So for continuous functions, we have the behavior of the function on the least upper bound of a chain must follow from the behavior of the function on the chain elements. From the behavior of the function on the chain elements. And this, in a way, gives some intuition why non-continuous functions are not computable, because, well, in our program, we essentially have just the chain elements, and they stand for the least upper bound of this chain. And functions should, well, the function can only look at these finite approximations of a recursively defined function, and everything should work out smoothly. So if I look just at these finite approximations, that should be enough to derive the behavior on the limit, on the least upper bound of such a chain. So all computable functions are, in fact, continuous. So continuous. So for that reason, it doesn't really harm if we throw out the non-continuous functions from our domains, because there is no program that can compute a non-continuous function. All programs should correspond to continuous functions. So the function domain can be restricted to just continuous functions. We don't need the other ones since they are not computable anyway. So now we have two properties. We have monotonicity and we have continuity, and the question is, how do they relate to each other? So we have seen that monotonicity does not imply continuity because we have this counterexample, but maybe the converse is true. So maybe continuity implies monotonicity, and indeed this is true. So the following theorem states something about the connection between continuous and monotonic. This is theorem 2.1.15. So this says something about continuous versus monotonic. Monotonic. So we have two domains, D1 and D2, with complete partial orders. So let these be complete partial orders on D1 and D2 respectively. And let f be a function from D1 to D2. Let this be a function. And the theorem says that if f is continuous, then f is also monotonic. And more precisely, it says that what do you need extra in addition to monotonicity in order to have continuity? So it says that f is continuous if and only if f is monotonic and something more. And, well, we know that continuous means this. So whether I first take the least upper bound and then apply f, or whether I do it vice versa, that shouldn't matter. And if we already have monotonicity, we need only one direction of this equality. So we only need the direction that if I apply the least upper bound first and then f, then I get something that is less defined or equal to the way when I do it the other way around. So normally for continuity I have equality here, but if I know that f is monotonic, I need only less defined or equal. The other direction follows automatically. And in particular, this means that if f is continuous, then f is also monotonic. So continuous implies monotonic. This is an immediate consequence of the statement in part A. And as long as all chains are finite, monotonicity and continuity is the same. So if D1 has only finite chains, then continuity and monotonicity is the same. So then f is continuous if and only if f is monotonic. Let's prove this. Okay, so let's first prove the direction from left to right. So let f be continuous, and we have to show that the stuff on the right-hand side holds. So let f be continuous. Now, if f is continuous, then clearly this holds, because we know that this here is equal to that, and, well, this relation is reflexive. So then f of least upper bound of s is identical to least upper bound of f of s, and therefore also less defined or equal by reflexivity of this less defined or equal relation. So this is trivial, but why is f monotonic? So we have to show f is monotonic. Okay, continuity says something about chains, but monotonicity says something about two elements. If we have two elements and one is more defined than the other, then, well, applying f to them should still keep this relation that one is more defined than the other. So we are only interested in two elements, say d and d prime. So let's look just at these two elements. So let d be less defined or equal than d prime. And we want to show that f of d is less defined or equal than f of d prime. Now continuity only says something about chains. So how can I get a chain from these two elements? Let's just put them together into a small set with two elements, and then this is a chain. So let's just look at the set consisting of d and d prime, and this is a chain. It's a very small chain, but it's still a chain. And now I know that f is continuous. Since f is continuous, I know that whether I first take the least upper bound of S, or whether I first apply f and then take the least upper bound, that's the same. So what's the least upper bound of S in our example? I have d and d prime. What is the least upper bound? D prime, because d is less defined or equal than d prime. So this is f of d prime. And what is f of S? Well, this is the set consisting of f of d and f of d prime. So what does this say? This says that f of d prime is the least upper bound of this set over here. So in particular, it's an upper bound. So f of d prime is greater or equal to every element in here. So in particular, it's also greater than this first element in here. So it means that f of d prime is greater than f of d, well, which is what I wanted to show. Now, if d is smaller than d prime, then f of d is smaller than f of d prime, or equal. So yes, continuity implies monotonicity. So this was the direction from left to right. Now let's look at the direction from right to left. So now we know f is monotonic. And we also know that f of least upper bound of S is less defined or equal than least upper bound of f of S. And so to show continuity, we have to show that the other direction of this holds as well. So what we have to show is that the least upper bound of f of S is less defined or equal than f of the least upper bound of S. And this is, if this holds as well, then by antisymmetry, these two things are equal. So this suffices by antisymmetry of the less defined or equal relation. Okay, so this is what we have to show. And how can we do this? Well, we have to show that the least upper bound of some chain here is is smaller or equal than this. So one way of doing this is we could show that this is also an upper bound of Fs. If this were an upper bound of Fs, then the least upper bound of Fs must be smaller than this. So it suffices to show that f of least upper bound S is an upper bound of Fs. Because if this is an upper bound of Fs, then the least upper bound of Fs must be smaller or equal. So let's show this. So if we want to show that this is an upper bound, we can take an arbitrary element from here and show that this is smaller or equal to this. So an arbitrary element in here means that we take some element from S and apply F to it. So let D be some element in S, and we have to show that F of D is smaller than this or equal. Now, why does this hold? Well, what do we know about F? We know that F is monotonic. This should be needed somewhere in the proof, otherwise this would be surprising. And, well, here we have F on both sides. If we look at the arguments, D comes from S, so clearly D is smaller than the upper bound of S. Since D is smaller than the upper bound of S, F of D is smaller than F of the upper bound of S, follows from monotonicity. So that's it. Okay, so now we've seen that continuity is a bit more than monotonicity. Continuity implies monotonicity, but we require a little bit more, and we have seen that there are indeed functions that are monotonic but not continuous. But this only happens if we have infinite chains. As long as all chains are finite, there is no difference between continuity and monotonicity. That's the statement of part B. And, well, why is it true? So if we have just finite chains and a monotonic function, I mean, the direction from here to here follows from A. So if it's continuous, then it's also monotonic. We've shown in A that this always holds, no matter whether chains are finite or non-finite. So the only interesting direction is the other direction, from monotonicity to continuity. So let F be monotonic. Let F be monotonic. And let's regard a finite chain. So if all chains are finite, then every chain looks like this, just from D1 to Dn. And if it's a chain, then I can order the elements, for example, such that D1 is less defined or equal to D2, and so on up to Dn. And what do we have to show? We have to show that F is continuous. And by part A, it suffices to show this direction here, because monotonicity plus this direction implies continuity. So by A, it suffices to show just F of the least upper bound of S. This should be less defined or equal than the least upper bound of F of S. So what's the least upper bound of this chain? Well, it's a finite chain, so the least upper bound is clearly Dn. And here we apply F to every element in S. So this is F of D1, F of D2, and F of Dn. So what we have to show is that F of Dn is smaller or equal to the least upper bound of a set which also contains F of Dn. Now that's trivial. The least upper bound of such a set must be greater or equal to every element in here, so also greater or equal to F of Dn. So this is trivial. And this element here, this element occurs in here, so it's obvious that the least upper bound is greater than F of Dn. Okay, so this gives us some information on the connection between continuous and monotonic. And as I mentioned, all computable functions are continuous. and therefore also monotonic. And therefore, we will now restrict ourselves to just continuous functions. So the domain for function expressions in Haskell will be the set of continuous functions only.
Does part A work if you put the inclusion in the other way? So f of the upper bound of S is more defined or equal to this upper bound of f of S?
You mean if the same thing is true if I turn this around? I don't think so, because okay, let's think about this offline, but I don't think this would work. I'm pretty sure that yeah, no, it doesn't work. So this totality function, this would refute it. The totality function is monotonic. The least upper bound of the totality function applied to fact 0, fact 1, fact 2, and so on. This would be bottom, and here it would be 0. So there, bottom would be less defined or equal than 0, and the function is also monotonic, but it's not continuous. So yeah, that's the counterexample. The totality function shows that this would be wrong. Okay, so we will now restrict the function domain to just the continuous functions. And before I do this, I have to wipe the board. So we will restrict the domain for functions to just the continuous functions. To just the continuous functions. And of course, the question is, will this still retain completeness? I mean, completeness means that every chain has a least upper bound, and we know that for functions in general, this holds. We've just shown this in a theorem in the beginning of the lecture. But if we restrict ourselves to a subset of the functions, then this is not so clear anymore, because it could be that there's a chain and it has a least upper bound, but maybe this least upper bound is not part of your subset. So is the set of all continuous functions complete? Functions still complete? I mean, the set of all functions is complete, but is the set of all continuous functions still complete? Not every subset of the functions is complete. For example, if I look at the set of non-total functions, that is not complete. The set of all non-total functions is not complete. Why not? Because I can have a chain of non-total functions like fact 0, fact 1, and so on. And this chain has a least upper bound, namely the factorial function, but the factorial function is not a non-total function. So this is a chain. It's a chain of non-total functions, but its least upper bound falls outside this set of non-total functions. But its least upper bound is no non-total function. So in other words, is the least upper bound of every chain of continuous functions again a continuous function? And the answer is yes, and this is stated by the next theorem, but I will skip its proof. It's just that we need this theorem to be sure that whenever we will change, there is still a least upper bound, and the least upper bound is continuous. So this says something about the completeness of the function domain. Completeness of the function domain. And it says that let D1 and D2 be complete partial orders on D1 and D2 respectively. Then the corresponding function domain is just the set of continuous functions from D1 to D2. So these angle brackets, this denotes the set of continuous functions from D1 to D2. The corresponding function domain is this. And if I compare functions by their definedness, then this is a complete partial order on the set of continuous functions. So what does that mean? That means that we have to show that if I only look at this subset of functions, so just the continuous functions, then there is still a smallest element, which is continuous, and every chain of continuous functions has a least upper bound, which is also continuous. So the proof means, here you see the definition of complete on the slide. So we have to show that there's the smallest element. And the smallest element is indeed the function that returns bottom for every argument. So this is this function from D1 to D2. And is this really contained in this subset? Yes, because this is trivially continuous. It's a constant function. Every constant function is continuous. Since this is a constant function, it is continuous. Since this is a constant function, it is continuous. And now the second part is we have to show that every chain has a least upper bound that is continuous. So let S be a chain of continuous functions. Then clearly this chain has a least upper bound. We proved this before. Then there exists a least upper bound. This is a function from D1 to D2. From D1 to D2. This exists by theorem 2113. 2113c. And it remains to prove that this is really continuous. It remains to show that this function is continuous, and this proof is not difficult but a little technical, and I will skip it here, but if you want to know it, it's in the course notes. So the proof that this is really continuous is in the course notes. It's not too difficult, but it's technical fiddling around with the definition, and I will skip this. And in this way we can finish the lecture in time. Otherwise, this would cost you another 15 minutes, I guess. Okay, so we have now seen how the domains look like. So the domain for every type, monomorphic type of Haskell, we have now seen what the domain is. For integers, it's that bottom. For tuple types, it's Cartesian product. And for functions, it's the set of continuous functions. Not all functions, just the continuous functions. And why this is useful, that we look just at the continuous functions, we will see in the next section, because then we will really define how to get from a Haskell expression, like a definition of factorial, to these functions, fact0, fact1, fact2, and then we can define the semantics of factorial as the least upper bound of this chain. And this will have something to do with the notion of fixed points, and we will do that on Monday. So see you again on Monday.